Yeah, I'm fine. I have joined. I don't know. So I am already there in the meeting.
Hello.
Yeah, good morning.
So, welcome all to this another session of the ongoing ATAL FDP. Uh, I am Mohammad Furqan, and I've been asked to introduce our guest today. Our distinguished speaker for this session is Professor Ashish K. Darpe from Mechanical Engineering Department of Indian Institute of Technology, Delhi. His research interests include vibration-based condition monitoring, noise control, fault modeling, and diagnosis of machine elements and rotor dynamics. He has been involved in various research-sponsored projects and industrial consultancy work. He has completed 9 sponsored projects funded by various agencies, including BARC, DST, Office of the Principal Scientific Advisor to Government of India, Naval Science and Technology Laboratories, DRDO, European Union, Aeronautical Research and Development Board, and Indian Space Research Organization. He is currently involved with 5 prestigious research and development projects in the area of sound and vibration. He has been consultant to various organizations and industries, notable among them Emery's Graphite and Carbon, Switzerland, Wärtsilä, Finland, Power Plate Inclusive USA, Delhi Metro Rail Corporation, NBC Bearings, GMR, etc. And he has executed more than 30 consulting projects. He enjoys supervising and working with his research students, and together with them, he has published over 100 research articles in journals and conferences. He has also filed 3 patents. He has supervised 12 doctoral students. Professor Darpe has organized 12 workshops and short training programs in the area of noise, vibration, and dynamics. Professor Darpe has been a guest scientist at Institute of Lightweight Structures, Dresden, Germany, between May and July 2003. He has also been visiting researcher at Knowledge Center of Smart Machines, PTT Technical Research Center of Finland, between May and July 2009, and guest scientist at Cluster of Excellence, European Center of Emerging Materials and Processes, again in Germany. Uh, he has been a member of the propulsion panel of Aeronautical Research and Development Board, ARDB. Professor Darpe has been founder director of a startup company called Silver Knight Technologies Private Limited at IIT Delhi. Professor Darpe is a recipient of JM Mahajan Best Young Teacher Award, Erasmus Plus Mobility Award, and he is a life member of Condition Monitoring Society of India. With this brief introduction, I invite Professor Darpe to kindly enlighten us with his knowledge and experience. Sir, please.
Thank you, Dr. Furqan. Can you please allow me to share my slide? Because, okay,
Sure,
let
sir.
me check. Yeah. Yeah, now it is done. Can you please confirm the slides are visible to you? To the participants.
Yes, sir. It is visible.
Okay, great. Thanks. Thank you, Dr. Furqan, for your kind introduction. I had, talked about bearing health monitoring in yesterday's lecture, and now today we will have an discussion on health monitoring of gears and gearbox. So this is also like a bearing an important machine elements, although not as in terms of importance, it is definitely similar, but no mechanical system is without a bearing, but you may have some systems without a gearbox. So gearbox is not as common as bearings, but definitely it is one of the important mechanical subsystem. And you will find the use of gearbox at variety of mechanical systems. So in some places, they form a very critical element of the entire system, and well-being and uninterrupted working of such systems are very important, in fact. So currently we are working on its diagnostics and prognostics for two important applications. Like one is the main battle tank and the other one is aerospace applications. So we again, like bearing, started with some basic laboratory based systems and evolved our understanding of the vibration in gearboxes, and whatever understanding we have through our students and faculty colleagues, I would like to share that with you. So like bearings, here also we mechanical engineer will tend to become a doctor of a machine, will try to assess the health by sensing important signals coming out of it. And the challenge there would be for him to extract information that is pinpointing to any anomaly in the system we are investigating. So if you really look at the signal emanating from such a complex system, would be as complex as the system itself, and therefore it's not that straightforward and simple to diagnose a fault in a bearing, in a bearing as well as in a gear. Right? So we'll try to understand a bit of the basic dynamics associated and the associated vibration phenomena. So at the outset, I would like to thank and acknowledge the contribution by my colleagues and my students. So prominent among them are the two students that you see at the bottom. Dr. Pradeep Kundu was with us as a PhD student. He was the first one who has done serious basic work on this gearbox vibration and its diagnostics. Manish Kumar, Dr. Kundu is now joining University of Cincinnati as a postdoctoral researcher. And Manish was a graduate student with us. He is now in DRDO lab in Bangalore. Professor Kulkarni has been my collaborator and a very close colleague, starting from bearings, and now he is faculty at IIT Bombay. All of them have really contributed immensely to my own understanding of this interesting topic. The outline of my talk today is I will just give you a brief, an overall framework of gearbox health monitoring, and then we'll look at fundamentally what actually is the responsible dynamics associated with vibration generated because of two gears in mesh, followed by some of the simulation studies that we have done to model a gear pair and a gearbox and what we can expect out of it. Then through Dr. Kundu's work, I will highlight some of the experimental investigations, and we'll pick up one of the very many topics that he touched upon and we investigated. So pitting diagnosis is pitting is a very common gear tooth flaw, and that we try to investigate and diagnose. So some preliminary results out of this would be shared, and we proposed a correlation coefficient based diagnostic parameter, so that would be discussed at the end. So again, why and how we really look at the gearbox vibration as an important activity in the overall maintenance regime. I had already highlighted this aspect of how important the diagnostics is in terms of keeping the availability and of any equipment as such. So we all need the downtime to be as low as possible. The machine should be available all the time. Its reliability has to be high. And this particular slide gives you an interesting failure statistic. And although this is belonging to a wind turbine gearboxes or wind turbines as such as a mechanical system, it gives us very interesting insight. Although it is applicable to this specific system, windmill, but it shows that although gearbox and some of the other elements have lower failure frequency, but the amount of downtime associated with their failure is huge, multiple times than other systems which fail frequently. So if it fails, it leads to a longer downtime and more cost associated. And so therefore, keeping it running without failure is very important. Okay, so that highlights why we should have proper monitoring system in place so that we have a better availability of the system. The other element or the other type of gearbox which we are currently investigating is in the aerospace industry. This is an aircraft mounted accessory gearbox, and so the input is from the turbine side, and then there are many accessories like pumps which are driven by the output shafts. And you can imagine if the failure of this gearbox happens, it would bring to a halt many of the critical subsystems which are connected to this. So therefore, the availability and the smooth working and avoidance of the untimely failure cannot be overemphasized, and it should be understood. Yesterday, somebody was asking about the gearbox and the helicopter failures, and this is one example that is not so long ago. In fact, the helicopter gearbox health monitoring picked up a lot in last couple of decades, last 10 years or so. There was a gearbox failure here and loss of 16 people in the accident. And right now, in the helicopter fleet, just like heart to a human being, the helicopter has gearbox as the most critical element. It is the heart of the main gearbox. It is at the heart of the whole system transmission chain, and any failure with that is catastrophic. So therefore, there are huge failure implications of a gearbox failure. What happens? What are the failures? Typically, although the breakage of the tooth is also seen and observed. For example, these are the actual gears from a transmission system of a truck, and you can see the chipping of the tooth as well as a severe degradation on the tooth profile. So these are of course much more severe and remain unattended till huge sound and vibration set in. But we cannot tolerate this to coming to this level, and therefore early diagnosis and early detection of such faults right at its beginning stage is very important. So moving on, as I mentioned to you, I will give you an overall framework of monitoring so that we have a clear idea as to what actually is happening in the whole framework. So you may assume this to be one of the gearbox which is getting monitored. What we typically would have is a sensor put on the gearbox, which is going to generate the data from the sensors. And this sensor data will have to be somehow pre-processed so as to remove some of the outliers which are very common in a practical measurement system. So these kind of outliers will have to be removed so that we have reasonably clean data to work with. We do not remove any of the information of the vibration. So raw time domain data is still preserved, except that some initial level pre-processing can be done. Then you have a basic time domain data available for processing it further. After that, you extract features. So even yesterday, we just discussed that, for example, in bearings, we do extract features from the time domain or frequency domain. So these are just tentative. These are not the ones which we typically use in gearbox anymore. But then such features which you are easily able to relate are listed here. That basically is the step associated with the extraction of the feature which can be correlated with the fault. So if the tooth gets damaged significantly, we expect that it will alter the peak value or a kurtosis value. And those features, therefore, if we trend it, you will be able to monitor any damage evolving. The other subsequent step could be classification of the fault, whether there is a pitting, whether there is a crack in the tooth, because pitting will evolve with a different rate as compared to a crack probably. So if you want to go further into RUL, it is quite useful to have fault classification done. Once you have done that, then either your physics-based or physical model-based RUL prediction models, or based on several data sets, you can have a prognosis done on the gears. And we can predict that if the current condition of the gearbox is here, then how long will it last in future? Okay, so setting a certain limit on the value of these features, you can figure out tentatively or approximately how long can it last. In helicopters, it would be interesting to check how many sorties it can carry out till you have to take it for the maintenance. Right? So these are all the algorithms that can be developed, which will lead us to understanding of RUL, and based on that, you can inform the maintenance crew as to when the maintenance is to be scheduled. So this is broadly the overall monitoring framework that we can design for this particular asset. Now, having had a brief outline of this framework, let's get down to the very basic thing, and similar to what we discussed for bearings, we can also look at how the gear pair behaves and what is it that cause a gear pair to generate vibration, so that we look at the vibration signal and extract information out of it. Just the way we took an overview of alternate condition monitoring parameters for a bearing. For example, you can use sound signals, you can use wear debris, you can use temperature and other operating parameters. Here also in gearbox, you can use acoustic emission, you can use sound, you can use wear debris, you can use temperature and vibration. But as we said yesterday, and it is very much acknowledged fact that vibration by far is one of the most common, most robust, most widely used parameter for assessing the health. So if that is the case, then it should be clear to us as to how do we, what do we expect a sensor put on a gearbox like this to generate or to assess or to sense the data, and what do we make out of it. So I shall get down to the basics of the gearbox dynamics and look at what kind of a vibration signal we expect from the gear pair when it is under the healthy condition, and how does that vibration signal change when it deviates or degrades from its healthy condition. So a gear box will have pair of two gears of typically of different sizes. And the way we discussed yesterday regarding the bearings, this gear pair and the mounting together can constitute again a vibratory system like a spring mass dashpot system subjected to an external excitation force. Obviously, for a gear pair, an external excitation force F of T, the simplest one could be an unbalance. But supposing if you take an idealistic situation, that typical governing equation of mx double dot plus cx dot plus kx equal to F of T, if in the idealistic condition, if we start presuming that there is no unbalance and therefore there is no external excitation to the gear pairs, we should expect theoretically no response, because when the right hand side term is 0, we cannot expect or should not expect any response x of t happening in case of a gear pair. But it is found that the gearing action itself is a source of excitation, and how is something which we should understand. So if I for a time being ignore the damping, and for the time being also ignore the external excitation force arising from the unbalance, let's say, what we have an interesting situation here is the torque is getting transmitted across the pair of these two teeth. And when the force is being transmitted from one to the other, the point of contact, all of us are aware in mechanical engineering domain, basic kinematics of the gears. We know that the point of contact actually slides from the tip of the tooth to the root of the tooth gradually as the transmission happens for one cycle of tooth engagement. So once the tooth gets engaged at its tip and the contact slides to the root, you now should imagine that this is almost like a cantilever beam. Exaggerated view here. A cantilever beam is subjected to a force at its tip. The stiffness of this cantilever, we all know, is given by this expression from basic solid mechanics. I think you should be able to recollect that. Now, if the effective length here of this cantilever is so much, and if the same force which is getting transmitted, when it slides to the root of the tooth, the effective length, this length is going to get changed every instant of time. So as the length is largest, we expect the stiffness to be lowest, and the cantilever at its full length has a certain level of stiffness K. Whereas if the point of contact slides to the root, the effective length diminishes, and a reduced length will generate a much higher stiffness. So when the motion take place, the stiffness continuously change and increase from tip to root as the contact cycle progresses. So that again brings us to this interesting condition here, that the stiffness here is not a constant stiffness, but is a varying stiffness condition. So what actually will lead this to? It will generate or it will cause the stiffness to change in a cycle, and you have a situation somewhat like this, that the stiffness changes in one cycle of oscillation, of engagement. The fact that the stiffness is not a constant, which typically we assume in all our basic governing equation for a vibratory system. These two are constants, but they are not. And the spring that we modeled to represent a pair of teeth in a connected gear, that spring is no more a constant stiffness spring, but a variable stiffness spring. That stiffness varies in a cycle of engagement of a pair of teeth. And that brings us to a very interesting change in this equation, that the value of K being continuously changing, we can treat this to have a mean stiffness value and some fluctuating component associated with it. So delta K is the fluctuating part of that stiffness, and you may have a mean stiffness. Of course, the mean stiffness is much higher than delta K. However, even if this delta K is small, that is good enough to generate this function, which is typically an excitation function for you, because this equation can be reformulated as mx double dot plus kmx equal to delta kx cos omega gt, which brings us the time varying excitation force delta kx, and that generates excitation to these gear pairs even if there is no unbalance in the system. In fact, this stiffness fluctuation is the one which is responsible for the vibration in gear pair and the gearbox. Okay, and all efforts are actually done in minimizing this fluctuation and then thereby reducing the vibration as well as sound. So gearbox sound is also annoying for high-end cars where rest of the vibration issues are taken care of, but the gearbox generates some annoying sound which the customers feel very annoying. Okay, so with this, let us again go back to what we were discussing for one engagement cycle. If it generates an excitation to this assembly of two gears, which would generate vibration in the gear, and we can assume therefore that because in one cycle of engagement of a pair of teeth, if this excitation happens, we may treat as a simplification one vibration cycle or oscillation for one tooth pair of teeth mesh. So one meshing cycle of these two gear pair would generate some oscillation, and as they go out of the mesh and when the next pair of teeth come in mesh, they will generate their own response and so on. So you will have as many such vibration cycles as the number of teeth on the gear and number of engagements in a gear pair. So this is how we observe that during one revolution of a gear, depending upon the number of teeth on the gear, there would be a similar number of oscillations, all related to the fluctuating component of the mesh stiffness. All right. Now, this is what will happen for a perfectly healthy gear pair in mesh with no other issues in the gear pair and the gearbox. All right. But things can become a bit complex if the gear is mounted, let's say, eccentrically, or there is an inherent manufacturing defect, and the location of the center of rotation and the geometric center are different. So what is expected then is that because of this eccentric motion in the gear, because it will be rotating about this, but the geometric center being here, it is going to create this eccentric movement of this gear teeth. And then what happens actually that the gear will try to dig into the pinion, and that happens once in one rotation. Obviously it will first dig into it and then it will come out and backtrack and then again go back. So this is going to take harmonically at the rate based on the number of revolutions per second of the gear. Now, what will happen because of this is that this gear blank will dig into pinion once in one rotation. So for one full revolution, this is how the variation in the response will take place. So now the gear is already having oscillations because of the gear tooth mesh stiffness variation, plus because of such problem in the gear mounting, you may have this kind of a situation wherein this motion will now get modified because of this action. And that modification actually causes the fluctuations to get modulated as per the digging in period of this particular gear blank. So the net effect here is now going to be the original variation in your this gear mesh stiffness, the gear mesh stiffness based response will now get modified by adding to this xa cos omega at. So this will now cause, instead of x cos omega gt, you will have x itself getting modulated and getting changed to this. Okay, so at each instant of time, not only your x, but because of this variation, both of them will get added up, and then you have the net response shown in this particular equation. So now the modified response is going to be what you see here in this equation. Is that clear to all of you? Now, if you look at this equation, I can reiterate this with perfect gearing condition. We expect only the gear mesh stiffness frequency related response. And now with the modulation happening because of the eccentric mounting of the gear, sometimes it may also because of the, although shown very exaggerated here, but if the gear blank is not perfectly circular, then you may also generate this digging in action twice in one rotation. So when this one digs in, then this one digs in. So you have that variation which we saw once in one rotation can change to twice in one rotation. So there are two frequencies involved. One is the gear mesh frequency, and then the other one is rotational frequency or its harmonic. So depending upon the waviness on the outer periphery, you may have higher frequencies appearing. Although that through manufacturing tolerances can be minimized to a great extent. But this is the equation that we saw in the previous slide. Effectively, so it so happens that either at a rotational frequency omega A or its harmonic twice omega A and the gear mesh frequency omega G, the entire response will take place with gear teeth being perfect, but imperfect gearing condition due to these kind of anomalies. That means such kind of typical assembly issues you may have, or manufacturing issues, you may have a situation which leads to this kind of a response. Now, if you simplify this or manipulate mathematically through trigonometric relation, the same equation can be written in the form like what you see. Taking cos omega gt inside, you are going to have these three terms from this equation. So one term is, of course, whatever is the amplitude, the frequency associated is gear mesh frequency, but then this product of these two cosine functions generate two frequency components. One is omega minus omega A, and the other one is omega plus omega A. That means one of the frequencies is going to be, this should be omega G and not omega. So this is omega G plus and minus omega A. So one frequency gets reduced from the gear mesh frequency by the modulating frequency. So this modulation frequency is the rotational frequency or its harmonic. So that is how in a gear machine, you will have such peculiar frequency components generated because of the gearing action. Now, if the same equation, if I can show in a frequency spectrum, so basically I am representing this equation in the form of response x of t, and if omega g, or omega in this particular case, so this is omega g and this is also omega g. So this is your omega g frequency component, supposing that the rotational speed is 10 hertz and the number of teeth on the gear are 27, then 270 hertz is going to be the frequency of gear mesh, of the gear mesh. And then these two components, omega g minus omega s, so they are going to be separated from omega g frequency. So this is going to be, the difference is omega a. So if you are operating at 10 hertz, then this 270 will be flanked by one frequency which is less by 10 hertz, that is 260, and the other one greater than 10 hertz, that is 280. So this is the kind of frequency response that we expect due to the gear meshing and the associated dynamics. So if there is perfect mounting of the gears, what you expect from the gearbox is the gear mesh harmonic signal, that is omega g. And these side bands actually are indicative not of the gear dynamics, but it is indicative of problems with the gear meshing or mounting of the gears. Of course, they also appear because of the flaws in the tooth, which we will be discussing shortly. But a perfect healthy gear would still generate a frequency that is gear mesh frequency. So the presence of this gear mesh frequency is natural and expected and is nothing to do with the problem with the gear. It is always going to appear because of the gear mesh stiffness variation. However, the side bands which are going to get generated, these are called as the side bands because they are on the sides of the gear mesh frequency. The difference between these two will actually tell us what is the problem or the source of the problem. If there is an eccentric mounting, then you will have 260 hertz and 280 hertz if gear mesh frequency is 270 hertz. And if you have an oblong gear blank, which generates 2 times digging action in one rotation, then instead of 260, you will have 250 here because 2 times the rotational frequency is 20 hertz. That difference is going to be then 250 and 290 hertz. That is again is going to be indicative of the problem associated. Now, having discussed this, we have been assuming that the gear mesh stiffness variation is going to generate a kind of a response that we assume will be with the frequency of omega g. Okay. Will it really be harmonic? Because here we are assuming the response to be harmonic, but only for the illustration purpose, I showed you that the gear mesh frequency related response is going to be harmonic in nature. In reality, it is not going to be harmonic because the variation in the stiffness itself is not harmonic. Okay, because we have seen in one of the slides that the gear mesh stiffness actually evaluated through mathematical process is going to be of this nature. So one teeth engagement will generate variation in the stiffness like this. The second one will be following it. The third stiffness variation because of the third pair of teeth, they will all look like this. So when the stiffness changes like this, you cannot say that this is harmonic. This is far from harmonic. A harmonic stiffness variation could have been this, like this. But it is not actually. It is this, and this is definitely not a harmonic variation of the stiffness. So if you do not have a harmonic stiffness variation, and it is repeating, so it is periodic. So when you, you all know that if you have a periodic function, that periodic function can be broken into series of harmonic functions, and that harmonic function would be integer multiple of the fundamental, and therefore you will have in this particular case we assume that omega g is the only frequency component, but because of this kind of a periodic variation in the stiffness, you will have several harmonics, and therefore in the spectrum you will get second harmonic of the gear mesh, third harmonic of the gear mesh. So this is going to happen that the second harmonic will appear, the third harmonic of the gear mesh will appear. Their amplitudes also of course will be different, and that is the typical output that we expect due to gear mesh stiffness, which is not harmonic but periodic. Now the moment we have x plus xa cos omega a t multiplied by the gear mesh related cos omega g t. So from the harmonic term multiplication, you will have, if omega g are multiple, that is omega g plus 2 omega g plus 3 omega g, all of this will generate several side bands. So about this there will be side bands, about this there will be side bands, and then your spectrum will look quite populated in that sense. So let us see what happens with this. We had calculated or evaluated numerically through FE simulation as to how the stiffness would change or would look like when the two teeth mesh with each other. So this is the way, almost like a rectangular function was shown. Of course, that was not more accurate one, which we later on analytically obtained through mathematical route, not the numerical one. What basically is this kind of a stiffness variation indicates that when we have a far from a harmonic variation in the stiffness, that basically would result into multiple harmonics. That's what I was talking about. If you have omega g frequency, you will have 2 omega g, 3 omega g, and so on. So all these harmonics of the fundamental gear mesh frequency, which is going to be 1 over this time, the time of engagement of one pair of teeth, that will generate multiple harmonics because of the nature of the variation of the stiffness, right? So now what we assumed initially, that it will be x cos omega gt, now you will have more terms to it because of the periodic variation, and therefore you will have x1 cos omega gt plus x2 cos 2 omega gt plus x3 cos 3 omega gt, and so on, depending upon how many terms you would like to consider. Now this would get multiplied to our normal variation in the eccentric mounted gears, and that would generate the side bands as we have discussed. Things become little more problematic when we assume that there is a deflection in the tooth, and the deviation from the involutive profile happens also because of a normal wearing of the tooth profile, or by pitting which can generate on the surface of the teeth. Those aspects will finally cause the signal to become this way. So a typical gear mesh waveform will not only have a gear mesh frequency, but many more components because of all kinds of problems and defects and variations in the ideal tooth profile. So now if we go back to the basic equations that we have been discussing, this is basically a emphasizing the kind of expressions that we usually end up with due to gear eccentricity. This is what we have already discussed. Due to with the perfect gearing condition, this is the gear mesh frequency. Due to tooth deflection, you will have a frequency of m omega g appearing, and many harmonics of it will take place because of the gear mesh stiffness variation. For even the healthy tooth with these tooth deflection, you may see that this particular part of this equation would appear in the the multiplication between this and this with the shaft rotational speed and its harmonics will cause a much more complex frequency spectrum, and that is how this spectrum will look like when you have multiple harmonics of the shaft rotation frequency appearing in the system. They will generate multiple sidebands. Instead of only one pair of sidebands, you will have multiple of them, as we discussed. And not only will you have omega g, the gear mesh frequency, but its harmonics also. And then each of these harmonics will have their family of sidebands. So you just add to that other structural vibration frequencies, the noise associated with it, the gearbox vibration signal are going to be absolutely messy, and a lot of frequencies do appear, and then it becomes a headache to extract useful information out of it. Fortunately, we do have techniques and approaches to clean it up appropriately, as long as you know what you're looking for, which is basically what we will see in the experimental work. Okay, so finally, if you have these kind of pits or damages on the gear tooth surface, you can also have frequency modulation taking place, because these engagements will not happen exactly at the same instant of time which you expect for an ideal gear pair with perfect involute tooth profile, but they will generate non-uniformity in the tooth spacing, and therefore the angular velocity of the gear will of course change, and that leads to frequency modulation effects in the gear tooth. So this frequency modulation would cause changes in the, because of the spacing changes, you have torque fluctuation taking place that ultimately leads to amplitude modulation also. And so you have an angular velocity change with time and frequency modulation also happening. They all feed back into the amplitude modulation. And finally, you will have all these kind of effects getting into the equation of its response. And all of these effects basically would generate sideband families in the spectrum, as we have already seen. So you have with frequency modulation sideband families the way we saw in the amplitude modulation, but in frequency modulation, the sideband families will be slightly different, but all of them will appear almost inseparable, both of them simultaneously being present, and becomes challenging to separate them out. Okay, so therefore, in general, what we should understand that when these sidebands and their amplitudes increase, they can be actually related to initiation and progression of the gear tooth surface faults. So what is important is not to look at the gear mesh harmonics or gear mesh frequency, but to more focus on the sidebands, because they are the ones which are actually resulting from the problems on the surface of the tooth. And this is what we are basically interested in tracking, because the gear tooth cannot be expected to be rigid in that, and there will be flexibility associated with them, which will generate these gear mesh harmonics. So gear mesh harmonics themselves may not be an absolute indicator of the problem, although the increase in their amplitudes do reflect some amount of mesh stiffness variation. However, it is the sideband and the amplitude or the strength of these sidebands which definitely caters to it definitely relates and correlates to a strong change in the level of tooth profile. And it's so whenever that tooth profile gets infested with pitting or spalls, these sidebands are the first one to rise in amplitude. So coming back to this mesh stiffness, how does it change although much more idealistic, a gear crack, a tooth crack like what you see in the bottom, will cause an overall reduction in the mean stiffness value. Whereas if you have a spall or some pitting on the flank of the tooth, it will create a deviation from a normal stiffness variation. As you see in the first cycle, that kind of a stiffness variation gets modified because of a spall, a big chunk of the tooth surface getting removed from the surface. Whereas a crack would cause us a definitive shift in the mean value, and that would result into a corresponding vibration. However, a more elegant approach would be to figure out what this stiffness is from an analytical formulation. So what we can do is whenever the force from the other tooth is acting on the gear teeth, a gear tooth from here like this, that would have a bending of the tooth and associated bending strain energy. It will also try to shear it off, so there will be shear strain energy. And then of course, because this is not absolutely perpendicular to the axis of the tooth, it will have certain longitudinal loading which will generate the actual strain energy. All these strain energies can be written, and then from that we all know from the basic materials, solids of mechanics, you can extract the force deflection relationship and then write the expressions for the stiffnesses. So you have stiffness due to bending, stiffness due to shear, stiffness due to axial load, and add to that, because the contact between the pair of teeth are typical point contact or line contacts, so you have a Hertzian stress, and Hertzian contact theory can be applied to have its own stiffness because of the contact stresses. So and because the contact is generating deflections in both the teeth, because both of them are flexible, you have the pinion and gear compliances added. Add to that the contact stiffness, that would eventually lead to an entire pair of teeth having certain compliance value. Okay, so a gear mesh compliance can be estimated by looking at all these strain energies, and also taking into account that the energy is stored in elasticity through both pinion and gear teeth. Okay. So having discussed this, let us look at how does the compliance change for the gear and teeth simultaneously. So as you can see, there are pairs of teeth which are getting into contact, but let us focus on this one. So as you basically have the rotation, if it is taking place in this direction, and this one is getting driven like this. So you may see that for a pinion, the contact is going to take place at its tip, and therefore at the tip you have, so in this particular case for a pinion, the compliance is going to be the least if it takes like this, if it is in driven gear. So if it is going to take place at its root, the compliance is going to be the least, and as it slides towards the tip of it, the compliance will increase gradually. So this is the way its compliance increases. At the same time, if you look at the gear teeth, then the meshing starts at its tip, and at its tip you will have highest compliance. The flexibility is maximum for the gear teeth at the beginning of the contact, and as the contact slides towards the root, its compliance continuously reduced to a minimum value. So both these pairs will have contrasting variation in the compliance function. And if you add both of them and take both of these together, this is what it happens. The compliance curve for the gear teeth will be looking like this during one engagement cycle, whereas Whereas for the pinion, it would be the reverse one. So it is going to go up like this. This one is going to come like this. The combined effect will create this kind of a variation in the compliance for one cycle of engagement. This is how the overall compliance curve for a pair of meshing teeth will look like. And if you inverse it, you will get a flip. You will basically get the stiffness of the pair, and that's what the stiffness would look like. The highest stiffness at the middle of the engagement and the lowest one at its ends. That is basically what you have, a variation in the stiffness. Once you have this variation, you can write governing equations with this variation captured in a mathematical form, and then simulate the response which is expected to generate. To highlight how this variation takes place for a more practical conditions where the contact ratio is not 1, that means we all know that in case of gears, you have typically more than one contact ratio value, wherein at certain fraction of the contact engagement cycle, you will have 2 pair of teeth in contact. For certain duration of the entire contact period, you will have only 1 pair of teeth in contact, and rest of the engagement cycle, you will have 2 pairs of teeth in contact. So what is interesting here is that when 1 pair of teeth completes their engagement, before the next pair of teeth or the third pair of teeth begins their engagement, there will be a period in between wherein only 1 pair of teeth are in contact. Okay? So this is actually shown here. So what you see here are 2 pairs of teeth in contact. So 2 and teeth number 1 and 2 are there. The motion is taking place like this. The contact point is currently here. The next gear from this side, teeth from this side, is now beginning in the engagement. So at this condition, you will have a pair of 2 teeth in contact. That means this is already in contact, and this one is just about to engage in contact. So there are 2 pairs of teeth in contact. We are going from this point onwards. So what you typically have is a situation where the gear mesh stiffness is corresponding to this location in the whole profile. Okay. As the rotation continues, you have a situation where this one, the point of contact sliding up there, and then it has come here, whereas this point of contact is beginning to go away, and now it is somewhere here. But here also, 2 pairs of teeth are in contact. So we are somewhere here, and then you can assume that the stiffness is going to be maximum here. As the rotation continues, you have now this pair of teeth almost about to leave the contact. We are almost at the end of it, and this one continues to slide up here. So we have this condition of engagement taking there. So we are almost at the end of 2 pairs of teeth always in contact condition. And after this, what happens? This is almost gone out of the contact, because this now teeth number 1 going out of engagement, 2 continues to have engagement with this one, and then you get into this location, or the stiffness suddenly drops because now the entire load is shared only by 1 pair of teeth, and this one is not contributing to the resistance. And as it continues further rotation here, there will be some period wherein only this particular pair will be in contact, and that is where later on this connection will be lost, and then you have only 1 pair of teeth basically getting out of this equation. Point number 2 is or the gear teeth number 2 is now sliding up. This contact will be reaching here, and now the next third teeth, which was here, is now getting engaged through this particular teeth. So all of this basically now changes to again back to two pairs of teeth in contact, and therefore the stiffness reaches to a higher value here. So we are now into this kind, and this process will continue to repeat. And so the point is, when contact ratio is more than 1, then instead of a stiffness which is varying like this half sine wave, is now going to be a sort of a rectangular variation, almost like a rectangular variation of the stiffness. Okay, so for one engagement cycle, instead of this, you will have this kind of a stiffness variation. All of that will change the amount of gear mesh harmonics that gets generated. So if you look at the entire one rotation cycle of a gear, typically, let's say for a contact ratio of 1.76, you can expect the contact the gear mesh stiffness to fluctuate as many number of times as there are number of teeth on the gear. So if you count these cycles, all these cycles will corresponding to each of the pair of teeth engaging and disengaging. And all of that will have a mean stiffness value, as I said, and a stiffness fluctuation amplitude, which will all generate the kind of modulations that we talked about if there are problems with the gear blanks. Now, having discussed the stiffness variation, so let me see, yes, we are halfway through. Having seen the gear mesh stiffness variation for a normal healthy tooth, but having a flexibility associated, which is a more realistic situation, we can also look at how the pits or spalls on the surface of the tooth can be modeled. So in the literature, people have modeled it like a pair of or a bunch of circular holes, blind holes, having certain depth, as you see here. So mathematically, they can consider each of these cross sections with reduced cross-sectional area. So the moment of area will change in each different location, and based on that you can revise the value of the stiffness whenever the point of contact slides through them. So this is how a flaw on the tooth surface can be modeled, and there are papers which are discussing that. So Manish, my student, modeled it more realistically because you cannot have a cylindrical drilled holes there. So a spall would look like almost like a part of a sphere, and based on the dimensional equations, he found out what is the effective moment of area at each of these locations, and based on that we can evaluate the change in the stiffness as the point of contact rolls. So the final culmination of that the analytical model and its corresponding stiffness evaluation would show up into this. So you have a healthy tooth, what you notice here, the kind of stiffness variation that it will generate will show up like this. Now, if you have some pits which are modeled on the tooth surface, there would be a drop in the stiffness value whenever there is a single pair of teeth in contact. So this higher stiffness will drop to a lower stiffness expectedly as the area resisting the load reduces because of the existence of such kind of pits. Now that will further degrade as the number of pits increase, and based on their location there would be a change in the variation of the stiffness during one engagement. So from here to here you have one engagement cycle of which is repeating. So at this part of the engagement cycle, two pairs of teeth are in contact. Here one pair of teeth in contact, and then in the rest of the cycle you have two pairs of teeth in contact. But they all together, this is one full cycle of engagement which will keep on repeating as the gear starts rotating. Now this would cause a change in the modulation characteristics because based on the variations in the stiffness during the engagement cycle, they will all influence the generation of gear mesh harmonics and the sidebands, particularly the sidebands, as we have investigated that. So this is how all kinds of configuration of these pits were modeled, and we figured out how it influences the response. Now, having because the gear mesh stiffness is the most central to any investigation, usually we spend a lot of time in correctly modeling the stiffness variation. Once that is modeled, we can bring them in the governing equations of motion. So what I'm going to discuss very briefly is how we brought that in the model of mathematical model of these gear pairs, and carried out numerical simulations and verified what literature stated, and then followed it up with investigations, experimental investigations to find out what kind of results we got. So in the lab we had this kind of a gearbox which is being powered by an electric motor. The braking load is applied by another DC motor there, which is connected to the resistance bank, so that it applies a braking torque on the gearbox. So we then modeled this entire gearbox as a discrete vibratory system, which looks like this. So one gear teeth, one gear on a shaft, and the other one on the other parallel shaft. The connection between these two is through a gear mesh stiffness. So this link actually represents a spring which is changing its stiffness continuously as the rotation takes place. The shaft of the gearbox itself is mounted in bearings, so you can model the bearings to be spring and dashboards. And so this is the entire model of the gearbox. We plan to also look at the dynamics of the casing or a box of the gearbox by looking at what kind of forces which are transmitted to the housing. But to start with, let us only focus on what kind of a response we expect to generate at the bearing locations or at the gear blank location. So we would be basically exploring what kind of vertical or horizontal vibrations that are generated because of such dynamics. So those who are conversant with vibration theory would immediately easily recollect the kind of mass and stiffness matrices it will generate. You have many degrees of freedom here, 2 degrees of freedom here for the gear, 2 degrees of freedom for the blank, plus the rotational degree also coming into picture because the ends are flexible or compliant, and that makes it multiple degrees of freedom system at a discrete system model. And accordingly, the stiffness matrix based on the stiffness variation or the stiffness model can be shown here. When we simulated this, this is what the response typically looked like. Because the stiffness is not a constant one, you cannot solve it analytically. So we solved it numerically by a numerical integration approach. If you focus on the steady state part of the simulated result, what you see is the gear mesh frequency and all its harmonics appearing in the spectrum. Okay. So 1800 is the gear mesh frequency, and then you have all the harmonics of this 1800 frequency appearing in the signal. So we did not excite the system with all these harmonics. We only modeled the stiffness as a time varying stiffness, and that is what results into this kind of a complex vibration waveform. If you convert it into a frequency domain, this is what you get, and it was expected that it would generate harmonics of the gear mesh frequency. if we introduce some pitting on the tooth surface, immediately a much more clean signal which has only gear mesh and its harmonics. I told you that when the gears are perfect but are flexible gears, teeth, blank is rigid but the teeth are flexible, and when it is transmitting such a large torque, it is expected that it will have some flexibility and will deflect without any problem or fault, neither on the mounting of the gears nor on the surface of the tooth. The response still generated gear mesh frequency and harmonics. It is all because of this kind of the stiffness variation that was modeled, which is expected in a typical gears. So without any problem, the gear vibration spectrum looks much cleaner, of course, with many harmonics of the gear mesh frequency. But the moment we introduce some pits on the surface of the gear tooth, so the gear tooth surface was modeled with some pits just below the pitch line, and those pits basically results in a changed spectrum. So apart from these gear mesh frequency lines, as you see, 1800, 3600, 5400, all of these frequencies. Apart from that, those frequencies do generate sideband families, and of course, because if you focus on certain frequencies, you can see that very neatly separated sidebands around the harmonics of the gear mesh frequency. So if this is 3600, this was 3550 because 50 hertz was the rotational speed. So they are neatly separated with and flanked by the sidebands. And these sidebands, as we know from the basic fundamental approach in theory, that these sidebands are indicative of problems in the tooth profile. So what we contemplated or conjectured actually appears when we model it realistically, and that's what is appearing in this spectrum. So now the question then becomes, how do we extract this information much more efficiently? Because these are all simulated results. The moment you look at the practical data, it will be much more complex than this. These sidebands will get buried in the noise and other frequencies, and becomes very difficult to decipher the presence, and that brings us into focus on processing of the data and signal processing of the vibration data. So Manish, my student, also investigated what we started with, that if the gear blank is eccentrically mounted and if there is an eccentric motion of that gear or a pinion, what does happen to the signal? So the position of these pitch points will change as the gear blank rotates with certain eccentricity. With that entire mathematical formulation, he figured out changes in the line through which the contact point slides, and with a very minute 250 micron eccentricity, what we figured out that the velocity ratio will fluctuate instead of being very constant as we expected it to. And that would create some changes. So as we see here, the amplitude of the time varying mesh stiffness, if you very closely see, there will be this kind of a variation. Okay, very minute one, but still noticeable, and that would cause modulation in the pinion response, and that would generate larger amplitudes of these sidebands, as you can notice very clearly here. So you have an amplitude modulation taking place and the corresponding increase in the sideband families here. So what again was sort of mathematically and conceptually we introduced during our discussion, the same is observed through simulation and actual dynamics of the system. Then another common issue that is very much possible in a typical gearbox is that the load torque will fluctuate depending upon the kind of load that you have connected it with. So if that happens, we model that also as a fluctuating torque. And again, you can see the fluctuating torque causes frequency modulation. You can just check how, how the, yes, how the frequencies fluctuate. So here you have the tooth which are having a different spacing in the stiffness variation, but later on as the torque drops and it varies, you will have the spacing between these cycles to be different than what it is there. All of that again generates both amplitude and frequency modulation, and you still again have changes in the sideband families taking place. So torque fluctuation and fluctuation in the eccentric mounting or a perfect mounting, deviation from the perfect mounting, they all lead to increased sidebands of the system. Please make a note that these gear mesh harmonics were still there whenever, even when the gear teeth were perfect in the sense they were without any flaw and the blanks were mounted perfectly concentric to the shaft and so on. So the moment we simulate these different operating conditions, we can expect the harmonics, the sidebands around these harmonics to shoot up. So that basically brings into focus the need for focusing on the sidebands rather than on the gear mesh harmonics. And if you have both these two effects coming simultaneously, you have these sideband families growing in complexity and so on. So separating out these sidebands and tracking them is the key to detecting problems and flaws on the gearbox. So all of these simulations were very useful in understanding the behavior of the sidebands, and so each fault or each problem can be easily investigated as a part of the process. Having done enough of these investigations, we will have a look at what the actual experimental data looks like. So we've basically developed a test setup in the lab, which was for carrying out a lot of experimental investigations on the pitting of the gear teeth. The good thing about this rig was it was designed to carry out large-scale experimental investigations wherein we did not actually introduce the faults artificially. That means the rig was developed for running it till failure. So we started with a fresh, healthy gearbox and kept on operating it till there was a clear indication that things are going wrong or vibrations have gone up significantly. It was also an excellent facility in the sense that there were provisions to periodically open it from the top. And Dr. Pradeep actually got a miniature camera to insert it in the gearbox and visually observe each and every tooth of the gears and take pictures of it, and after periodic inspections we were able to correlate then the physical damage with the actual response data or feature data. So this is the close-up view of this gearbox. We rigged it up with many sensors. These sensors, as you can notice, if you can see here in this picture, there is a sensor placed here, there's a sensor placed here on both input side as well as on the output side here. there were not only the accelerometers, as you see here, but we also used partly acoustic emission sensor on this. There is a torque sensor, as you see, an inline torque sensor, which was recording the torque fluctuations. And this particular cover can be removed, and you can insert, actually through this, we used to insert a miniature camera to take pictures of the tooth profile. Yeah, so I think if you really see, this is the acoustic emission sensor, although I will be discussing and focusing more on vibration data. So 2 acoustic emission sensors were placed. There is a key phasor signal, which is there from this, which is basically to record once per revolution reference signal, which also comes handy for the kind of feature extraction we planned for this case. So a typical vibration signal, one of the vibration signal is what you see here on the top. So, oh, sorry, this one gone too far on. Yeah. Yeah, so this part of this total signal is shown zoomed into this area. So that pertains to 1 full revolution. You can see that although there is some periodicity which you see, it is all infested with other frequency components as well. It's not looking like a pure harmonic signal. And in this particular case, we make use of a reference signal. So this reference signal gives you an idea as to when, during which period of time, 1 cycle of rotation is getting completed. Now, what is the use of this key phasor signal? In case of a gearbox, particularly when you have multiple stages of transmission. So suppose there is 1 gear pair here, and then there is another gear pair here with the different teeth, number of teeth, and then you have another one here. So what will happen is, based on the speed of rotation and the number of teeth on this gear, this particular pair will have a certain gear mesh frequency. Okay, so let's say 1. This pair will have its own gear mesh frequency because the speed is different, the number of teeth may be different. So you will have a different frequency here. There will be a different frequency corresponding to this. Now you have already seen that for a single pair, you had multiple harmonics and multiple sidebands here. Okay, you can imagine what will happen on the same spectrum if you get another family of gear mesh frequency and harmonics of different frequency values and their own sidebands. Another one from this. All of this will clutter up and make the spectrum so complex to decipher that it will be almost impossible to extract useful information out of it. So what is therefore done in practice, that you take a reference signal for rotation of this particular shaft. So if this shaft rotates 1 revolution in, let's say, 0.3 seconds, then this is the pulse that will generate after every 0.3 seconds. Or in terms of time, I'm saying, but it is more precisely and more correctly, I must say that this will repeat after 360 degree of rotation. So after every 1 full rotation, a signal will be generated from the sensor, which is basically put to generate the reference signal. Now, what happens in this particular case, that if you take several samples of 1 revolution data from this original data and average them out, slightly additional steps are involved, but just for the sake of simplicity, what I'm saying is, if you take equal 1 rotation sets of data and average them out, okay, so this is added to this, this is added to this, this is added to this, and you average it out. what happens is those frequency components which are not synchronous with rotation, okay, that means that if they are not integer multiple of this rotation of this shaft, they will balance out to zero, or they will average out to zero, because they will not be synchronous with this rotation. So supposing that if there is one rotation in this particular cycle, but there is another frequency component which has a different time period, then when you average this part with this part with this, all of them, this kind of a component will eventually become zero in the averaging process. All those frequency components which are synchronous with the rotation of this shaft will get emphasized and which will get retained, and all the components and frequencies associated with the rotational frequency of the other shafts will become zero or will get minimized to a great extent. So this approach is called as time synchronous averaging, and it is one of the de facto most common approach of initial pre-processing of the signal. So I will show you how this has resulted in a better signal output. So as you see, this one rotation, this another rotation, this another rotation, all this data when we average out, each one taken from here, second set from there, third set from there, and then you average it out. Each time it is resampled with the angle domain and so on. Ultimately, you will get an absolutely clean signal, as you see here, almost harmonic one. And in fact, you can actually count the cycle. So you have one peak, second, third, fourth, fifth, and so on. You can count, you will find that these cycles are exactly equal to the number of teeth on this gear. This gear of ours was having 53 teeth on the blank, and we obtained, this is an experimental data, this is not a simulated data. It's a time synchronous average data of the experimental signal, and you see exactly as many number of cycles as there are teeth. So each cycle here is representing one engagement of a pair of teeth, and that is what you get a very precise data, very pertinent data, because this is the data on which we will be working on. This data, therefore, removes not only from the other gears, of course, in this case, there was only one gear pair, but then you also get vibrations from the structures, from the foundation, all of that gets cleaned up by the time synchronous averaging. So then, having done this, what we did was, because all these problems in the gear teeth contributes to the side bands, we thought that we devise a parameter which will take into account the sideband information much more efficiently. So what we proposed was, if we take an initial signal in the time domain, and all other later signals, if we find the correlation of that later signal with respect to the original signal, we would be in a position to understand the correlation between the later signal from the healthy signal, and whenever the signal deteriorates, that signal will have less correlation from the original signal. So the correlation coefficient as a parameter was proposed to be investigated or used in understanding whether it will be useful in diagnosing or detecting problem. For example, here the level of modulation appears to be less, and later on as the defect progresses, if the modulation characteristic changes, then the correlation of this original signal with the new signal will deteriorate, and that will get captured properly. So that was the idea here, that a metric like a correlation coefficient was basically proposed. Now, it is important that this signal which we are trying to find correlation between should be a signal which captures the modulation characteristics, both frequency and amplitude. So therefore, we need to use not a original time domain data, or not even the data which was with the gear mesh frequency, because gear mesh frequency is not an indicator of a problem. So what we did was basically to see if these modulations are increased, what happens to your correlation coefficient parameter. So as the modulation was increased, that means by increasing the amplitudes of the sidebands around the gear mesh frequencies, what actually happens? Okay. The correlation coefficient value of a time synchronous averaged signal started dropping as you change the modulation characteristic. All right. Now, what we also done was by removing the gear mesh frequency from the spectrum and then finding out the correlation coefficient. There is a nice monotonous decrease in the correlation coefficient value, unlike this kind of a correlation coefficient, which was done on an original signal without removing the gear mesh frequency. Now, you must remember and recollect that these sidebands are the problems or indicative of the problems, not the gear mesh. Now, gear mesh frequency becomes dominating in the entire spectrum, or it tries to dominate the signal. So if you remove the gear mesh frequency from the signal, in fact, gear mesh frequency and all its harmonics from the signal, you are left with only the sidebands. And because all of this is time synchronous average, you have already removed some of the noises and the contribution from other frequency components or from the other sources. So you are left with only sidebands in the signal, and then you start taking the correlation coefficient between the original data, healthy data, and the data that you gather later. So we have seen that as the modulation amplitudes, if you increase gradually, the correlation reduces and deteriorates as we expect, because the new signal is not highly correlated with the original one. And therefore, this can form a better diagnostic parameter for damage detection. So this is just an example, the computed values of the correlation coefficient of the original time domain signal, original in the sense time synchronous average time signal. It shows that after certain data points, the CC value, change in the CC value is increasing, but it is not monotonous in its change. Whereas if you do that correlation coefficient after removing the gear mesh frequency and its harmonics, so that's the signal that we call that is as a residual signal. So correlation coefficient of residual signal, residual in the sense we remove the gear mesh harmonics from the signal. Then what we are left with is a residual signal containing only only sidebands. Now, if you apply correlation coefficient on that residual signal, then the incremental drop in the correlation coefficient value keeps on increasing, and that basically generates a monotonic variation and much more sensitive as compared to the original signal. Okay. We also tried to evaluate the damage correlate the damage by actually visually observing and recording through camera pictures what is the pitting area. So through a software and taking the pictures, we calculated what is the cumulative total damage area across all the 27 teeth that we had. And you can see these pictures which are properly correlating to a continuous increase in the pitting area. And you may notice that the CCR, which was calculated from the measured experimental data, that had a decreasing CCR value, continuous decreasing CCR value, and larger the damage, lower is the CCR value. So if you keep trending the CCR, it is possible to diagnose how the defect is progressing in this particular case. Now, through this rig, we generated a very rich set of experimental data. Almost 6 experiments run to failure were carried out. Nowhere in the past literature you will see any work which has generated such a huge amount of data, all because of persistent efforts there by these candidates. He generated almost 8 experimental test setups. What you see is a monotonic decrease in the CCR value in all these cases. You can see that almost every time there is a continuous drop in the CCR value. And the parameter, useful parameters are those where you generate monotonic trend. The parameter should not generate, like we saw yesterday with the case of kurtosis. The kurtosis does not generate a monotonic trend. Okay? So this is what we observed in this particular case. Now, in terms of its comparison with other established parameters, which were already investigated in the past, what we
Sir, we are unable to listen.
am I audible now?
Yes, sir. Yes.
So need to connect it to the power here. So I was discussing and explaining you this particular table where we compared our parameter CCR to the other established parameters. And we found that it does much better.
Excuse me, sir.
Yes.
I think you have to share your screen again.
Oh, is it? Just a minute. Let me do share that. Okay. Can you see this screen now?
Not yet, sir.
Can you see that now? Can you see that because I have shared it already.
No, we are not able to see.
Okay, let me try it again. So it says share file, but okay, share file. should be able to share the window, right?
Excuse me, sir.
Yes.
Yes. What did you say?
I was saying that the way it happened last time, it is not allowing me to share the screen. I don't know why. It is asking me to share the file, but there is no point in sharing file. I should be able to share the screen here.
So let us just try. I think there is some bandwidth issue.
But see, I clicked on share, but it is not allowing, it's not displaying the screen for sharing it. It only says share.
चले गए.
Okay, can you hear me?
Yes, sir, we can hear you.
Okay, and can you see the screen?
Not yet, sir. It is opening. It's showing that that it is still in the process.
Okay, okay. Let me wait for a minute. Maybe it will come. I don't know whether the network is slow from your side or from my side. Please confirm once you are able to see.
Sir, it is showing. I mean, on your screen, on your window, it is showing that due to low bandwidth, video is not able. It is not able to play the video.
Oh, okay, so let
Okay, maybe
me.
you can switch off your video.
Okay, okay, I can do that also. Yes. I will. Okay, so video I will stop and just let me know if you're able to see the slides. Can you see the slides
Not
now?
yet.
Not yet. So one possible option now is that I can change my network to another option. So I'm doing that right now. I will shift to another network.
Okay. Change कर रहा है. Yes, sir, we can see it now.
Okay. So I'm back to my home network. So, yesterday there was problem from this network, so I started with my mobile network today. Anyway, so what I was discussing is there were other alternate features which has been used, which have been in use in the past. So we compared our new parameter with the others, and you can see that while some parameters were either increasing or decreasing at different levels of the severities. Uh, in contrast, there were consistent and much higher level of change, and that's why this parameter has that it is both monotonic as well as more sensitive compared to other parameters. So this table actually reiterates that aspect. So once this was shown, we also, as I showed you in one of the slides, when I showed you the setup, there was an inline torque sensor that we also used, because we were thinking that if there is a problem on the tooth surface, it might influence the torque which is getting transmitted, particularly the fluctuation part. And so what we did was we tried to track the torque fluctuation with time, and then this is what the result from one of the experiments, or two of the experiments. So in both of these two, you can see a gradual increase in the fluctuation in the torque as the damage increases on the tooth surface. So torque can also qualify to be a good parameter for trying to investigate the health of the gearbox. We also use temperature, and in yesterday's lecture, I mentioned to you that the temperature is another parameter which can get influenced both for bearings and gearbox. But here, what you notice that because the gearbox was required to periodically stop and start, the temperature change, was having these kind of drops, and then it used to take time for it to grow, and there was no consistency and a nice trend as such on the temperature variation. So this temperature variation may not have been or may not be a good parameter for a very sophisticated monitoring approach. So this particular figure shows what somebody was asking yesterday about the sensor placement and orientation, and that's what you see from our rig picture. You must have seen and recollect that the sensors were placed at different locations. So they were placed both in horizontal location, vertical location, both at the input side of the gearbox as well as on the output side of the gearbox. So if you see, this is like horizontal orientation. This is the vertical orientation of the sensor. This is in the output side. This is at the input side. So we took the data from each of these sensors so that we understand and explore what is the correct location, what is the more optimum location, more appropriate location to place the sensor. So it resulted in a monotonic and much better result in this horizontal orientation of the output sensor. So the sensor should be placed on the output side preferably, because in other directions it did not show as good sensitivity as others. Although in all cases it had a reasonably good trend, but output location, output shaft location in the horizontal direction turned out to be better as compared to others. So this is where I summarize my talk. What we discussed in this particular talk is how the gear mesh stiffness actually varies and is the important vibration source for the gearbox vibration, and how this stiffness variation actually is influenced by presence of faults, how it generates modulations in the signal, which are basically important source for identifying degradation in the gearbox. It also, we discussed how the operating conditions like fluctuating torques, improper assembly, all of that can lead to modulations, and how it does that. If you have eccentric mounting, they do influence the modulations. We also looked at how a vibratory model can be developed for such gearbox so that we can investigate the signal from the gearbox. What was not discussed and is currently being investigated, how the forces, dynamic forces going into the bearings, how it will excite the gearbox casing actually, because the sensors are typically placed there. But because our measurements did do the measurements very close to the bearing locations, dynamics of the gearbox casing was minimized, and therefore placing of the sensor should not be away from the bearing locations in the gearbox, as close to the bearing, so that you get rid of other influences as much as possible. It cannot be minimized, it cannot be reduced to zero, but can be minimized to a great extent. What we also discussed as to how this simulation exercise is useful in building up the framework for the diagnostics, which basically can get refined from experimental observations and so on. So this is all what I wanted to cover in today's session. And as we did yesterday, we are open to questions now from the audience. So Dr. Fukran, maybe you can moderate I cannot see their comments here. I do not know why, but you can let me know if there are questions. I will be happy to answer.
Yes.
Them.
So there are a couple of questions from the participants.
Mhm.
First one is from Rahul Kumar Sinha. So he is asking, sir, please explain hunting tooth and ghost frequency and how to identify that and what causes ghost frequency to appear in spectra.
Okay. So the ghost frequencies typically are a result of manufacturing issues, because what we have all the time talked about in this case is the gear teeth, which are perfect involute, but when they are actually manufactured, typically through hobbing process, the issues or inherent tolerances and those hobbers, they do have their own issues, and they basically get transferred to the manufactured teeth. So the source of the ghost frequencies typically come from the manufacturing. So there is something which is associated with the manufacturing of them.
Barrett is asking, sir, can we consider spline shape for pit or spall?
What shape?
A spline shape.
Spline shape for spalls.
For pit or spall.
Yeah, so pit is, I can show you some pictures where the pits were, okay, let me go back to my slide and show there the profile of those, a second. Let me, all right. So the actual measurement of those pits could generate a profile which is not a regular one. Depending upon how the micro cracks grow, they can be of this shape. So to model a pit either by the cylindrical blind holes, as has been done by many people in the past, is far away from the actual pit profile. But we tried to model it using sort of a part of a sphere here as an example, to make it easier to evaluate the change in the stiffness. But in reality, as you see here, it is much more irregular, and from place to place it can change, because in this case it could be this. If the crack, micro crack, suddenly dislodges the piece, it could be like this. So it is very difficult to standardize a pit profile as such. It can vary a lot, and therefore any profile that matches roughly with this kind of variation in the depth should suffice. And the most important part is, even if you refine this to a standard profile, a slight variation will not influence what ultimately gets reflected in the response, like the sidebands. They would have a minor variation in their strength and the quality. So a pit profile, as long as it matches with roughly this kind of variation in the depth, should suffice, in my opinion. Was there any other question associated with
Yes,
this?
there is one more question from the same person. So this time he is asking, for gearbox defect, is bearing considered as healthy one?
Yeah, that's a nice, interesting question. So our next target is to bring in the bearing issues also, along with the gearbox modeling. And as you must have seen in this model, this is precisely we try to make the model so that these bearing issues can also be simultaneously included. So this mathematical model, or a simplified vibratory model, had already the bearing model like a spring dashpot. Now, if you want to bring into account or bring in the bearing issues, you can do that by making a modified model of the support. So, but what you are saying, yes, true, it is true that in the gearbox bearings and their issues should also be simultaneously addressed. But through the process of data processing, we can actually remove the bearing effects through the signal processing, so that the contribution from the bearing problems on the gearbox vibrations can be, I mean, you can filter out the gearbox or a gear pair dynamic related signals wherever it is influenced from. We can focus on that particular part of the signal. And if you then filter out this particular signal from the overall signal, you will be left with only bearing related signal. That also is one possible option, that whenever you have a bearing problem generated, because your sensor is closely sitting here, it will be able to capture any changes in the gear health. So it would be interesting to observe and figure out what gears or gear vibration gets influenced by the changes in the bearing dynamics. But it is true that in gearbox, bearings are also critical, because you imagine that if this gearbox had a misalignment problem, and then the misalignment between the motor and the gearbox, or from the gearbox to the load, if that has alignment problems, it will cause heavy stressing on the bearings, and the bearings will deteriorate in its health. So bearings also create an important source of vibrations for the gearbox. True that. I hope I answered his question. If he has any counter question or any other supporting question, please let me know.
Okay, so I think there are no more questions here. Yes, so he is typing, that person is, I think, trying to respond in the chat box.
I don't know why am I not able to see your chat box, because then I
He's
can
just saying
immediately.
thank you, sir,
Okay.
for your answer.
Meanwhile, sir, I would like to thank you for your talk, and it was again a very wonderful session and interesting and knowledgeable session. Sir, I know the time is up, but I just want to know something from yesterday's talk. If you allow, can I ask?
Please go ahead. Please.
Yes, sir, in one of your case studies, where one of your project works, you have shown the case of a turbo pump. So I just want which was operating at quite high speed, more than 30,000 RPM.
Yeah.
So I just wanted to know, sir, which kind of sensor was used for its measurement, like data acquisition? Was it a non-contact laser sensors? Because in the picture I couldn't figure it out, and I'm interested to know about the high-speed measurements.
Okay. Yes. So we used a vibration sensor. So it was a conventional sensor, not a laser-based measurement. The sensor that you saw, probably the one which was there in the picture, was basically for reference measurement. I think reference signal measurement. But yes, because we were investigating also the foreign particle ingress in the raceways, because that was also one of their problem areas. So we were also measuring the shaft vibration signal through a non-contact displacement probe. So what you would have seen there was a non-contact displacement probe, eddy current probe, as well as there was a vibration sensor on the housing. And of course, for reference signal, we were also using a tacho sensor. All three of them were parallelly used. So we need to be careful, because the vibration sensor range is limited.
Yes, so that is why I wanted to know if and was that stud mounted, because as shared by Dr. Piyush's talk, the mounting affects the range of frequency being captured. And generally, yes, sir.
Yeah, please go ahead. Yeah.
Yeah, so sir, if I just want to know that if we go for glue epoxy
No,
connection,
epoxy glue more
that
than 1000 hertz.
y
Yeah,
y
more than
yes,
1000.
yes, sir. So
Yeah,
what kind of again connection was that? Stud connection possible? I mean, and
on
few cases
that,
not possible. Yes.
yeah, that was basically a stainless steel kind of a structure which
Yes, sir.
uh,
Yes, sir.
was difficult. So we had to use some kind of a fixturing device which was a very hard kind of a glue on top. So let me open that picture. Let me, yeah, I think this is it from
Yes, sir.
yesterday.
Yes, sir. This one. Yes, sir.
So yeah, so there was yeah, so this was basically tacho sensor. So it was only for measuring the RPM from a reflective tape. These two are basically non-contact displacement probes which we got from um, this company Micro Epsilon, which are not traditional Bentley Nevada kind of sensors. These were slightly high resolution and high sensitivity non-contact probes. So we do have a few of them in the lab. So during that time, what we wanted was also that they were facing issues in the seizure of these pumps because of solid lubricant in the bearings, because they use at the cryogenic conditions the solid lubricant. So the raceways are coated with that, and then as uh, heat develops, it generates debris, and that maybe sometimes generates seizure or vibrations. So this was also, so in the bearings we introduced these foreign particles also. That was different activity, and those results I did not present here, but the idea was also a couple of BTech students worked on that problem of how to diagnose foreign particle ingress from the vibration data. So they produce some interesting results. So we used orbit plot generated through these orthogonally placed non-contact displacement probes, because this is directly seeing the vibration of the shaft. Of course, practically there are issues because you cannot have such kind of sensors directly seeing a shaft. So there are issues, but then we only wanted to investigate whether there is a, in principle possible to diagnose such foreign particle ingress. So to cut that short, the answer to your question is we could not stud mount these sensors on this. They were mounted at certain location down with a hard glue. But these ones are isolated. So this fixture is basically directly seeing the shaft vibration or excursion of this vibration. And they are basically measuring the orbit vibration, I mean orbit plot. So from the shaft vibration, we plot the orbit plot. And the RPM is through this tacho sensor. So this is Monarch tacho sensor that we used with a reflective tape. I
Okay,
think,
sir. Thank you. Yes, sir.
yeah.
Thank you so much, sir.
I was just trying to see whether I have another picture where there was an accelerometer. So we used, I think, triaxial sensor here.
Yes, sir. Yesterday I observed, but again, triaxial sensors, do they have such high range of frequency? I mean,
So now you can see that roughly 40,000 RPM will also generate, so maybe how much, 500 hertz, so about 600 hertz or so. So a sensor which is having its resonance frequency, in our case the resonance frequency in one of the sensor was about 32 kilohertz, and the measurement range of the triaxial is also 8 to 10 kilohertz in the measure direction. So if you have your rotational speed close to 5 to 600 hertz, even if you look at your bearing defect frequencies and the structural resonances here were of the order of few kilohertz, they were not going beyond the accelerometer's measurement range. In fact, as I discussed yesterday, high frequency resonance technique or an enveloping technique will still be able to make use of those resonances, even if they are generated through the accelerometers themselves from the data that is getting generated. So in that sense, the lower frequency range of the rotational speed and bearing defect frequencies were well within the measurement range of the accelerometers that were used. But HFRT or enveloping data, we can still use the resonances generated in the sensor themselves, apart from the bearing housing. Yeah.
Thank you, sir. Thank you so much, sir.
Any other question from the attendees? See anyone?
Rahul Kumar Sinha has one question. Yes, triaxial do have high range capability up to 40 to 45 kilohertz. Sorry to pitch in, but just wanted to share my thoughts. So it's just a comment, I think.
Thank you,
Not a
Rahul.
question per se.
Thank you so much for your information.
I mean, the triaxial that we have in the lab has in one direction about 8 kilohertz, in another direction about 10, 11 kilohertz. So I haven't seen, maybe I'm ignorant on that, but I haven't seen a triaxial going that high in the frequency range. 40 kilohertz is too high. But maybe I have not seen it or have not come across it, probably.
I think Dr. Furqan, you may please conclude the session.
Yes. Yes, okay. So thank you very much, sir, for taking time out and sharing your extensive knowledge on the subject with us. With this, we would like to conclude this session, and we will gather at 2 p.m. For the next session, which is from industrial side. So an industry resource person will deliver a talk on emerging trends and challenges in condition monitoring of industrial machines. So for that, we will gather at 2. Let us disperse for the lunch break. Thank you.
Okay.